Shivas here, and today I'll be talking about what are transformers and how do they work. So this is going to be quite a long video, as you can probably see from the YouTube timestamp. Yeah, but I will be going through apparent paradoxes that I have thought about, and I will resolve them, and we'll get down to the bottom of how physics works, or at least how the intuition behind the physics works. So what are transformers and how do they work? So most of it, if you are from high school, then you probably would have learned that in a transformer is made out of two coils, right? One is called the primary and one is called the secondary, and then they are two coils, so they're coils of wire, and they have a certain winding ratio. In this case, let's say they have 1 to 10. Okay, then you learn that the primary voltage is then equals to the ratio of the primary voltage to the secondary voltage is then equals to the ratio of the windings as well. So this would imply that voltage of the secondary is equals to 10 times the voltage of the primary. So this is a basic fact, right? And then however, we will then hear that current of the primary to the current of the secondary is inversely related to the winding ratio, and this would imply that current of the secondary is actually lower than the current of the primary. So with the two facts together, they would say that this is due to the conservation of energy, and namely the power on the secondary side is equals to the voltage times the current, and since by these ratios we can ascertain that is equals to the voltage of the primary times the current of the primary, and that equals the power of the primary side. So then this is just conservation of energy, meaning that whatever power you put into the primary side, you get out from the secondary side, and that assumes that it's a perfect, it's an ideal transformer. So yeah, naturally, one question that when I first learned this, I asked was that how can the voltage on the secondary be higher than the primary, but the current on the secondary is lower? So it's like if we have V equals to IR, right? Then if you have a higher voltage, how can and assuming the resistance doesn't change, how can the current be actually lower? It seems to, isn't it the case that your current should increase? Okay, so that is one question. Okay, then the second question is that okay, so to answer the short answer is that it still holds, but in each circuit, meaning that the primary side and the secondary side are actually two separate circuits, so you cannot think of them as related to one another. The only relation between them is the ratio of the voltages. So yeah, so in each circuit, Ohm's law still holds, but if this is unconvincing, then please watch on. So the second question that I then thought of was that the teacher would then say the power loss is equals to I squared times R, and I is the current, and if we want to keep, and if I is low, then power loss is low. So this is something that you might have heard. Then this is resistance of the power line, right? It's wasted. So this is the power wasted, and they want to say that if I is low, then the power loss is low. But one question that I then had is that if this is true, then isn't it also equals to V squared over R? And if V is high, then power loss is high. I was very confused at this point, but don't worry, we'll later see that this is actually a completely wrong perspective when we think about what actually the formula means. It's actually not the voltage of the secondary side, it's actually the voltage across the power line. So actually this is the voltage across the power line. But don't worry, later we will see this diagram over here. You see this diagram over here with the primary here and the primary here. So later you see that this is the V is actually the voltage across this power line. So it's entirely possible for the current to be low, and then the voltage across the power line to be low as well. This voltage does not refer to the voltage on the secondary. So that is the difference over here. And yeah, so okay, so how do I want to make this video? I want to make this video through a series of examples. So I will have 4 examples. The last one will be answering this question. Okay, the last one will be answering this question, and the last one will be an application of it to the power transmission system in the world. So example 1 is going to be talking about we're going to learn how to do calculation, okay, in a circuit, and we're going to learn some stuff also. Example 2 is then going to be so-called communication, or rather example 2 is going to be source or load. Okay, so we're going to think of it'll make sense later. Okay, so number 3 is going to be communication between coils or the primary or secondary sides. The 4th one is going to be application to power network. Okay, so with the first example, we'll be going through a calculation in a circuit. So this is within the A-level syllables. So okay, I'll tell you what. Okay, so the first one is going to be numerical. The second one is going to be intuition. The third one is going to be intuition also. And the 4th one is going to be a little bit of both. It's a bit of numerical, a bit of intuition. Yeah. So the reason why these 2 intuitions over here, they are backed by equations. Remember that physics and engineering is always backed by the calculations, and you must base the intuition, base them off the calculations, so that you don't develop false intuitions of what might happen. So they are backed by equations. Okay, so always refer to the equations, but the equations for these are a bit harder, so I will not be going through in this video because you need to spend quite a lot of time to study it, and maybe another video perhaps. But I will drive through the intuition, which will at least help you roughly understand why. But if you want to understand it at a deeper level, you always need to go back to the equations. There's no running away from it. Okay, but hopefully this will at least give you some guiding idea of what actually happens from a perspective of someone from someone who have gone through the equations and developed an intuition that I feel is useful, and hopefully you'll feel is useful too. So okay, so anyway, without beating around the bush, let's go on the first example. So with the first example, we have a transformer. It's a 1 to 10 transformer. Okay, and the primary side is connected to an AC source of 10 volts. Then the secondary side is it's connected to a 10 ohm component. Okay, so we want to ask the question of what is the voltage on the secondary. What is the voltage on the primary? This is the primary side. What's the current on the primary? What is the voltage on the secondary, and what is the current on the secondary? So there'll be a few equations that essentially govern this entire system. The first one is that the voltage across the secondary is equals to the current on the secondary times the load 10 ohms. Okay, then the second one is going to be Vs over Vp is equal to 10. So this is Ohm's law. and we'll see that Ohm's law is actually not violated, then this one is going to be transformer formula, I guess. And then the last one is going to be conservation of energy formula for the currents. So yeah, so from these three equations we can figure out all these quantities over here. So how? Let's just get started. So for the first one, we know the voltage of the primary is going to be 10 volts because of the very fact that it's connected directly to the source over here of 10 volts. So from that we can find the voltage of the secondary through this formula, which is going to be 100 volts. Okay, so after that we can then use the Ohm's law. We can then use Ohm's law for the secondary side to find that is equals to Vs over 10 ohms equals to 10 amps. Yeah, so 10 amps. Okay, and then lastly, for the primary side, we can use this one. We know the secondary current, so the primary current must be 100 amps. And so we see that this number one, power conservation holds, energy conservation holds, because this side, how much you have how much okay, I'm really hesitant to say power because there's something called reactive power, but this side is 1000 watts. Okay, and on the secondary side, yeah, it's 1000 watts or so, and the 1000 watts is basically transferred from the source through this transformer into the load. So it's basically important to identify what is the load and the sources over here. So this guy over here is the load and is now drawing 1000 watts because there's 10 amps flowing through it and there's 100 volts across it. And then this guy is acting as a source. Okay, it's acting as a source of 100 volts and is delivering a current of 100 amps. And then this guy is acting as a load because it's actually receiving 100 amps from the AC source over here. So you see that the green stuff is labeled as sources and the yellow stuff is labeled as loads. So yeah, so actually that ties in nicely into what I want to illustrate in the second example. So in the second case, so example 2, okay, so before we go on to example 2, let's just summarize what we did for example 1. So summary, how to do calculations. We learned how to calculate stuff using Ohm's law and other rules such as conservation of energy. So this is just a simple example, and we see that lesson is that Ohm's law is actually not violated. Now, as a short segue, you might be wondering, wait, hold up. If Ohm's law is not violated on the secondary side, okay, that's fine because Ohm's law is not violated on the secondary side. But isn't Ohm's law violated on the primary side? Because you have a 10 volt source and you're drawing 100 amps. But what is the resistance? Isn't the resistance 0? Because assuming the wires are ideal conductors, then wouldn't that imply that shouldn't your current be equal to infinity? Well, no, the current should not be infinity because there's actually something called impedance. There's something called inductive impedance. So this is basically, what is the idea of impedance? The impedance is basically a resistance for AC circuits. So yeah, so the impedance is basically the resistance for AC circuits, and inductive over here basically means coil. So a rough overview of how this works. Okay, before I give you an overview, let's take a look at the Wikipedia example. No, sorry, not Wikipedia. Let's take a look at Google. So this inductive impedance, this is the best answer I can find, the intuition. So this is just the intuition. Of course, it's backed by equations, but inductive reactance or impedance is the name given to opposition to a changing flow current. The impedance measured in ohms, just like resistance. And in inductors, voltage leads current by 90 degrees. So don't worry. So actually, inductive impedance leads to something called phase lag as well, where your current, your voltage is like that, right? And in a normal circuit, your current in a resistor, in a purely resistive circuit, your current is also proportional to voltage. So current for purely resistive circuit. Okay, but for a circuit that involves inductors or capacitors, which is out of the scope of this video, it's actually there's actually a phase lag. So when you have sinusoidal waves, they can have different phases. It's sort of like translation in time. So it's for inductive. So there's something called phase lag, but we won't get into too much details. Basically, basically the current and voltage are not always in sync in some sense. And this leads to something interesting actually called reactive power. And reactive power is not exactly power that is delivered. It's sort of the power is sort of sloshed back and forth from the source and the load, because for some areas, for some parts of the transmission, the power is transmitted from the source to the load, but for other in another half cycle, the power is actually transmitted back from the load to the source. Sort of like how you charge up a battery, then when your charger dies, the battery sort of returns the energy to the charger. So yeah, anyway, that's about phase lag. So sorry for the digression, but what I wanted to say is basically when we say Ohm's law is not violated on the secondary side clearly, but you may be wondering why it seems like Ohm's law is actually violated on the primary side, but it's actually not violated. I'm telling you, because there's something called inductive impedance that acts as a resistance. So yeah, so in this case, the inductive impedance would be 10 over 100, which is 0.1 ohms. So 0.1 ohms of inductive impedance. But anyway, that's a digression, because I do not want to get into inductive impedance in this video. But you can check out my other video. I think it's called Physics Olympiad 3, Oscillations and Waves. I did talk about LRC circuits over there. So if you want to go into the mathematical details, then by all means. But anyway, so that's example 1, how to calculate, and Ohm's law is not violated. So example 2, source and load. So this is actually sort of nice. It's sort of extension from the first case. We see that the green ones are actually the sources and the yellow ones are the loads, right? So what if you have a more complex system? How do you determine what is a source and what is a load? Well, the answer is that you need to see what is connected to them. So if you have a transformer and you connect a source, this is a source to one end, then the end actually, the end, in this case the primary, becomes a load. And if this one is a load, then the other one, that is the partner, is actually the source. So this would, from the perspective of something else connected, let's say a resistor, from the perspective of a resistor, it would see this coil as a source, as something that's providing it energy. So what is a source and what is a load? A source provides energy, or rather current, and a load receives energy. This is just the intuition. Yeah. So you may be wondering, what if we have the same transformer, but we connected the source to the other side? Then would that flip? And the answer is, of course it will. So in this case, now this one is a source, then this one becomes a load. And then this one is a source, and whatever is connected on the other end is a load. So the key takeaway over here is that okay, so before we go to the key takeaway, let's draw more example of a bigger example. So in a more complicated scenario, the same rules apply. So regardless of what the winding ratios are, they can be anything they want. Okay, you can even have 3 windings coupled together, but let's not get into that. So if you have this end connected to a source, then green is a source that drives this load, which turns this one into a source, and then this one is a load, and this one is a source, and this one is a load, and this one is a source, and then whatever is connected on the other end will be some load. Okay, so okay, now you may be wondering why is this the case? Well, it's due to magnetic coupling, or rather it's due to Lenz's law or Faraday's law. So magnetic coupling, and the physics law that it comes from is Faraday's law. Faraday's or Lenz's law. So the idea is that if you have a coil, okay, and you apply an AC signal to it. Okay, so you put a source over here, then you are driving a current through this thing. So you are driving a current I, and in so doing you are creating a magnetic field. So this coil over here, it creates a magnetic field that is oscillating actually, because this is an AC source, right? So the magnetic field is a oscillating magnetic field. And when you have an oscillating magnetic field, there's 2 effects. Okay, number one, it induces an EMF. So we know that oscillating magnetic field induces EMF, right? So it actually induces an EMF in both the primary and the secondary. So in the primary side, this oscillating magnetic field has 2 effects, one in the primary and one in the secondary. So what role does it play in the primary? It creates an EMF to oppose change in current. Oppose the current. And for the secondary side, it creates an EMF to turn secondary into a source. So actually this ties in nicely with what we talked about just now. Remember that I mentioned that there's something called inductive impedance. So there's something called inductive impedance. And what is this inductive impedance? It's a resistance for AC circuits. So where does this resistance come from? It comes from this EMF. So let me explain. When you have an oscillating magnetic field, it creates an EMF in this side across the coil it creates a coil that opposes current. And what else opposes current? Resistance opposes current. So in some sense, there's an effective resistance created due to this EMF. So this EMF, it creates this effective resistance because it acts to reduce the current that's flowing through it. And in fact, this this so-called resistance is called inductive impedance. It's given by this formula. Okay, inductive impedance is this XL thing, is equals to 2 pi f times L, where f is the frequency and L is the inductance, something like a resistance but for coils. So there is, in a sense, when your EMF, because you have an oscillating magnetic field, and that an oscillating magnetic field only occurs in an AC circuit. So when you have an AC circuit, you create an oscillating current and an oscillating magnetic field, which creates an EMF because it's changing, because the magnetic field is changing. And this EMF opposes current and leads to a sort of an effective resistance that is called inductive impedance. Yes, so I hope you caught that, but don't worry if you didn't. But essentially, I just wanted to say that this oscillating magnetic field, it ties in neatly with this inductive impedance on the primary side. Now on the secondary side, what do we see over here? We see that when you have an oscillating magnetic field, some of the magnetic field lines cut into the secondary coil, so the secondary coil experiences a changing magnetic flux as well. And this changing magnetic flux, it creates an EMF across its two terminals. So it creates a changing EMF across the two terminals that make it look like a source. Okay, so it looks like an AC source from the perspective of whatever's connected on the other side. So yeah, so then the question of is a inductor a source or a load, or rather is a transformer a source or a load? The key is this: if you as in the inductor, the coil, if the coil is the one providing the magnetic field, then the coil is a load. So for example, in this case over here, which one is the one that creates the magnetic field? Well, it's the primary side, it's this side, it's the yellow one. So in this case, this guy is the one that draws current, and hence this is actually seen as a load to whatever is on the other part of the circuit. So whatever is on the other part of the circuit needs to provide this coil a current to create the magnetic field. However, if you are the one receiving the changing magnetic field, then you are a source, because if you are, imagine you are this secondary coil over here, this longer one, you are not the one creating the magnetic field. Someone else is giving you the magnetic field, and that someone else is precisely the other side of the transformer. The other side of the transformer is creating the magnetic field and is saying, oh, let me leak out some of this magnetic field to you. And you are saying, oh, I see this magnetic field, thank you very much. Using this magnetic field, I can create an EMF, and hence you essentially get an EMF from someone else. So this energy transfer from a load to a source is precisely communicated or done through this changing magnetic field. So if you are the secondary side, you just observe this magnetic field created by someone else, and hence you have an EMF. And when you have this EMF, you can drive other stuff in the other part of the circuit. So you can drive a load, and hence you are a source. So I hope that I've explained this part clearly. Yeah, so yes, so that's the rule of thumb. So in the end, that is actually the summary for this example. The thing I wanted to say is that whether you are the source or the load, the intuition at least is going to be who supplies you the current and who supplies you the magnetic field. If someone is giving you a magnetic field, then you have an EMF and you are a source. Whereas if someone is giving you a current, then you are drawing current, you are taking in current, and you are the load. So yeah, this interplay between who is the source and who is the load is quite important in terms of understanding. So now, of course, one curious question that you might have, which is very good if you have, is that what happens if I connected two sources, sort of this thing like that? What happens in this scenario? Will the world explode? Would it? Well, the answer is that you will need to work out the equations. So you depend on things like how much voltage is on both sides, how much voltage is both the sources supplying. Then in some sense there's going to be an interchange of energy to and fro, and then you have to write down the equations, like minus LdI dt of the primary minus the mutual inductance, and yeah, I don't want to get into it, but just as a glimpse of it, it's a differential equation and then you need to solve things. So what happens if it's not a straightforward scenario where you have one side is the source and one side is the load? What happens if you have both sides is like sort of connected to the source itself, so both sides solve the load in a sense, then they are still supplying each other? Then you need to turn to the equations. Okay, so yes. So with that, I conclude example 2. Let me just drink a sip of water because my throat is kind of dry. This is my second draft already. Okay, so very good. Yeah, so third example. How does... Okay, so third example, let's say I'm a little AC source over here. I'm living my happy own life. Then somebody connects me to a transformer. Okay, I'm like, oh, what the heck, man? Okay, fine. I need to give you some current. So then, from my perspective, from the AC source's perspective, the only thing that it sees is this. The only thing that it sees is this guy over here. Okay, the only thing that it sees is this guy over here. So it's gonna ask the question of, yo, how much current do you want? How much current do you want? Then how do we answer that question? Well, now the primary side would then say, oh, okay, I don't really know because I need to ask my partner. So the secondary side will say, oh, let me check. So instead of just drawing whatever current it wants, it needs to check with its partner. And what is the partner over here? Partner is going to be the other side of the transformer. So this transformer would then say, oh, okay, somebody's asking me, so I need to ask how much current. So how much current? And then the side over here would then say, okay, I am a resistor and I need this much current if you have this much voltage. So what is the point of this example? Seems kind of ridiculous, but essentially this communication is done through the differential equations and is done through the magnetic coupling. And the magnetic coupling is this term over here. Okay, this coupling term is the term that tells that communicates the primary side to the secondary side how much current is going to flow in the entire circuit. So as an example, what will happen if the resistance of the secondary side fell? Let's say this resistance fell. Okay, so let me just highlight the mechanism that goes through and how this fall in current over here will lead to a rise in current, how this fall in resistance over here, fall in resistance will lead to a rise in current. So if R falls here, how would it lead to an increase in I? So the process is done through, the first thing that occurs is that when you have a fall in resistance, because we know the voltage across the primary is the same, and it remains the same, and the voltage across the secondary remains the same, so the current through the secondary side would then increase. Okay, so when the current increases, essentially, if you write out the equations, which I don't want to go into detail, but let me just highlight what happens if you do write out the equations. If you do write out the equations, then when your current increases, then this term increases. Okay, this term increases because you're changing current is higher, and when you're changing current is higher, then the impedance when your current so what happens when the current is higher? It creates a stronger opposing magnetic field. So the magnetic field created by the secondary current, okay, the secondary current would create its own magnetic field, and it would interact with the primary side as well. This magnetic field would then decrease, and when this magnetic field decreases, the effect is that the load, the impedance over here falls. Okay, why does the fall in magnetic field cause the impedance to fall? You need to look at the signs, the signs. You need to look at the plus or the minus of the equations, and you'll see why. But I'm just saying that the impedance of the load over here falls, and then since the voltage source remains the same voltage, it supplies at the same voltage, the voltage doesn't fall, so the current must have increased. So then the current would increase, and that is why the current increases in response. That's why the current increases in response to a fall in resistance here. So as for exactly how the process happens, it is through the equations, but this is the intuition behind it. Yeah. So yeah, and as you can see, so the key takeaway is here is that key takeaway is that how does this signaling occur? The signaling occurs through the magnetic coupling, because the primary's magnetic field cuts into the secondary. So the primary's magnetic field, which is caused by the primary current, would affect the secondary side, the secondary EMF and the impedance and stuff, and the secondary's magnetic field will also affect the primary's magnetic field. So primary, so the effect of this magnetic coupling here is that the primary current affects the magnetic field generated by primary, which affects the EMF of secondary, and on the other hand, the secondary current affects the magnetic field by the secondary, and because they are coupled inductors, then it affects the EMF of primary. So once again, in summary, when the resistance over here falls, the current increases. We know the current increases. Okay, the current increases. When the current increases, then the secondary current affects the magnetic field created by the secondary, which then affects the EMF of the primary. It's a both ways direction. So it affects the magnetic EMF of the primary, which causes the EMF of the primary, the resistance, the so-called resistance to fall, which in turn increases the current through the primary. And this increase in current through the primary would then increase the current through the secondary to account for this. So which one happens first? Does the primary current or the secondary current increase first? I would say that they happen simultaneously, because in the end, when you write out the equations, it's a self-consistency sort of equation. They sort of both happen simultaneously. So yes, so that's example 3, and with that, let's tackle our final example where we'll be looking at the application of transformers in a home network. Right, so now we'll move on to our example 4, and this is the case where we really see a real life application of how transformers can be useful in achieving higher efficiency. So efficiency is sort of the measure of a useful power over the total power used, which then the total power is going to be equals to the power lost plus the power that's useful. So essentially we want to reduce the loss. We want to reduce the loss to increase the efficiency. So okay, so how do we go about doing this? Let's just I will go through two examples. Okay, one is without transformer, and the other case is with a transformer. So you'll see in this case that the efficiency for without the transformer is pretty bad, whereas the efficiency for with the transformer is actually pretty good. So how about let's just draw some diagrams. So let's just say that we have a, so this is the power, the resistance of the power line. Okay, so because our power lines are made of copper and other metals that don't have a perfect conductivity, they will always have some resistance that will lead to power loss. So this essentially causes power loss, which is bad. So we want to minimize this power loss. But how do we do so? Well, later we'll see that with the transformer it will help a lot. So this is the first case of without the transformer. So this is the first case. So let's say we have a resistance of the home. So this is the resistance of the home, which is used to do useful work, useful power. So for example, your washing machine or your lights or your oven, yeah, stuff like that. So let's just say this is 9 ohms, okay? And let's say that the power generator is 10 volts. 10 volts AC circuit, AC source. So it's an AC source of 10 volts, and so we can easily calculate the current. What is the current? Is the total resistance is going to be 10 ohms, 9 plus 1. Okay, there are two loads over here, so the current is just going to be 10 divided by 10 equals to 1 ampere. So 1 ampere flows through the entire circuit, and in the end your power loss is going to be equals to I squared R. So 1 ampere squared times 1 ohm, that gives you 1 watt, and your useful power is going to be P useful is going to be 9 watts. Okay, so in the end the efficiency is equal to 90%, which is not bad, but we'll see later that we can actually improve this greatly. So yeah, so the key takeaway over here is that when looking at, in order to minimize the current, okay, so you can see that how we may ask the question, how to minimize the current. Because if we minimize current, then we minimize losses through I squared R. We minimize the losses through I squared R, and we minimize the current, then we can minimize the total power loss. So how do you minimize the current? Well, we could use a home. So solution, maybe a possible solution is to use a home with higher resistance. You see that if your home had a resistance of, let's say, 99 ohms, okay, let's say R home was equals to 99 ohms, then your current will equals to 0.1 ampere, and then your power loss would then be 0.01 watts, whereas your power useful is then your power useful will then be 0.99 watts, and then your efficiency is hence 99%. So you can see that by raising the resistance of the home from 9 ohms to 99 ohms, we effectively raise the efficiency. So the key to note here is that we care about the ratio of the we really care about the ratio of the resistance of the line to the resistance of the home. We want this to be as huge as possible, okay? Because that will lead to a higher efficiency. The higher this resistance is, the higher the efficiency. This is actually easily seen because it's just a voltage divider, right? If you have a voltage divider, then yeah. So okay, now the issue is, how do we do raising? If I make you buy a house and I ask you, hey, can you raise the voltage of your raise the resistance, sorry, can you raise the resistance of your appliances to something else, then clearly that might not work, because maybe your appliances cannot work with 0.1 amps. Maybe they just need more current, they just need the 1 ampere that is originally the case. So maybe I can't simply force my citizens to use appliances of lower current, because the fact of the matter is that things like washing machines, they consume a lot of current. So what's the ingenious method that comes into play? The method is called transformers. So the upshot of this, okay, the upshot, if you don't understand what I'm going to say soon, the upshot is we can use transformers. So we can use transformers to so-called artificially raise the resistance of the home. So how do we do that? The answer is with inductive impedance. Okay, so let me just illustrate what I mean. So this is your power plant. Okay, then it goes through something called a step-up transformer. So we require 2 transformers to do this magic. A step-up transformer, then it goes through the resistance of the power line, okay, which also equals to 1 ohm, the same. Then it goes through something called a step-down transformer, and finally into the home. So let's just say that, okay, initially we had efficiency 90%. Let's see if we can improve it. So we set the resistance of the home to be 9 ohms. So you see the 9 ohms. Remember that this one, without the transformer, it was 90%. Okay, so just keep that in mind. We'll come back to that later. So without the transformer is 90 ohms, 90% efficiency. Let's see if we can achieve better. So this is once again 10 volts. And so yeah, so let's say the ratios are 10:1, okay? And so what's the first step over here? The first step is to calculate the voltage on the secondary. So okay, so we know that this voltage over here is 10 volts. So this voltage over here is also 10 volts. Then we have this end, which has a voltage of 100 volts because of the 1:10 step-up ratio. And 100 volts like this. Okay, so what is the key here? So there's 2 loads over here. One is the resistance of this line, and one is this side of the step-down transformer, the left side of the step-down transformer. So the magic over here is that in order to artificially raise the resistance of the house, we need to pick a step-down transformer with a high inductive impedance. So how do we do so? So the inductive impedance is actually affected by a few factors, and one of it is the number of turns. So if we pick a high number of turns, then your inductive impedance would turn out to be greater. So let's just say we managed to construct the inductive impedance, a transformer with the inductive impedance of 999 ohms. Okay, so this is the inductive impedance here. So then what is the current through this circuit? Now we see that this one and this one has formed a 1000 ohm in total. So your current is actually pretty small, it's 0.1 ampere. Okay, and that's great because that means that the power loss is then only 0.01 watts, right? So your power loss is only 0.01 watts, and then so you have power loss of 0.01 watts, which is great. But then let's take a look at what happens. Hold up, because we can't celebrate yet. We need to think of how much current actually goes into the home, because if you have 0.01 watts but your current going to the home is only 0.1 ampere, then that's not good at all. But we will see that the magic comes in from this step down transformer over here. So what happens over here? Well, the fact that you have 0.1 ampere flowing through this means that there's 999 volts across this end. So there's 999 volts. Okay, and because of this step down ratio, then on this end you have a source of 99.9 volts. And in the end, your home it sees a 100 volt source. So in the end, your home has currents of just 99.9 divided by 9, which equals to 11.1 ampere. So that's your current. So yeah, so then what's the power useful? It's going to be 99.9 watts. And if you calculate the efficiency, then you can see that it's pretty good, man. So you have 99.9 over 0.01 plus 99.9. And what is that? That is almost 100%. Yeah, in fact, it's 99.99% to 2 dB. So so the upshot of this is that, but you see, right, by choosing a transformer, a step down transformer with a relatively high inductive impedance, essentially we have appeared to raise the resistance of the home, and the left side of the circuit, it doesn't know what the home's resistance is anymore. The left side of the circuit, it simply sees the high impedance load over here, and it says, oh, you're such a high impedance guy, fine, I will give you a little bit of current only, because you are so high resistance, and voltage divided by resistance is hence going to be very low, so it's 0.1 ampere only. And when you give 0.1 ampere only and it goes through this power line, then your power loss is going to be very, very small. However, when you have such a low current, that isn't useful for houses, because your houses require tens of amperes. So that's why you go through the step down transformer. So upshot of this is that step up transformer, it goes from low voltage, high current, to high voltage, low current. And on the other hand, step down transformers go from high voltage, low current, to low voltage, high current. So you see that the demands, the houses want high current. However, your power loss wants low current. So in the end, how do you balance between high current and low current? Well, you can't really balance the two. It will end up being a trade-off. So instead, you go through this intermediate step of when you're when you're going to meet the power line, then you say, okay, sure, you want low current, I'll give you low current. Okay, so along this line, this power line is happy. It sees a low current. It wastes little power. Whereas when your houses then say, hey, I want high current, then you feed it a high current by converting it to a high current low voltage signal through the step down converter. And how does this happen? Well, remember, and this happens through the inductive impedance. Precisely through this inductive impedance are we able to fake a high resistant load. So yeah, essentially that's the crux of it. And so okay, so that returning back to some questions that we had. So one question that we had was if P loss equals to I squared R is equal to V squared over R, then how come the I can be low while the V is supposedly high? Well, actually, that's not true at all, because the 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 V over here, remember the V over here and the I over here refers to the voltage across this component. So this voltage is the voltage across this component, and the voltage across this component is very low. It is the voltage across the secondary side that is high. Okay, but the voltage across the secondary side does not fall solely across the resistance of the power line. So most of the voltage across this secondary side falls across this end. So it's our voltage divider. You see there's two components, 1 and 2. So the upshot of this is that the key idea is that most of the voltage falls across here instead of here, and as a result your voltage here is across this component is very low, and that's why you can achieve a low power loss. So there's no apparent paradox here. We have successfully resolved understanding, and we see that the V squared over R actually refers to the voltage across this guy. So, and yeah, so your current is low, your voltage is low, power loss is low. So another question we had was that how can you have high voltage and low current on the secondary side, on this side? Well, you can have high voltage and low current if you have super high resistance, right? That makes sense, right? So you have a super high resistance, which is in the case over here. Remember that we have 999 ohms over here. This is a super high resistance. So very little current flows through this part of the circuit. Very little current flows through this part of the circuit. And yeah, and so that really answers the question. If you just consider the big picture, then Ohm's law holds in all cases, and there's no apparent violation of Ohm's law, nor the conservation of energy. And then the final question we have is, then okay, we didn't ask this initially, but we can ask this now. So so how can the home receive high current again? Because remember, over here in the middle we have a very low current, and this low current it cannot power a house. However, you do know that the voltage that falls across this end is very high, so that's where you convert it to a low voltage high current, and then your home can take all the current at once. So yeah, so I hope that that really clears things up. Yeah, I feel much clearer after figuring this out, and I couldn't really find a good resource online. So if you did enjoy this video and you really learned the better conceptual picture of transformers, please leave a like and subscribe, and a comment to be greatly appreciated, because it's really encouraging to see that my videos can help people. So yeah, so with that, that's the end of the video. I hope you have a nice day and happy physicsing. Bye.